Bearcats, this is Unit 2, the Pre-Cal Review, and we're going to start with 1A, and in this we're asked to find the zeros of the function algebraically. Finding zeros mean we're going to set our equation equal to 0, and as you already know, when we find those zeros, which are also called solutions, so you could be asked to find the solutions or the zeros or the roots or the x-intercepts. They all mean the same thing. So finding our zeros makes a lot of sense when you set it equal to 0. So it's like taking this equation and saying equals 0. All right, now first thing I look at, this is a quadratic, but I see that not easily can I multiply or factor out easily information. I've got a coefficient in front, I've got some large numbers, so I am going to use the quadratic formula in this one. There is also no greatest common factor. I'm always looking for that, as there was a GCF to factor out, but there is none. So I'm going to go ahead and use the quadratic formula. Just to remind you, that is negative b plus or minus square root b squared minus 4ac all over 2a. All right, and in this problem, our a value would be 3, our b value would be negative 16, and our c value would be 21. All right, let's go ahead and just substitute in. I'm going to go through the math pretty quickly. If you need extra help with that, you probably want to do a little extra practice on your own. But I'm going to go ahead and plug into the equation. So a negative 16 would be positive 16 plus or minus the square root of 16 squared, or negative 16 squared would be a positive 256. Minus 4 times a, which is 3, times c, which is 21, all over 2 times a, which is 3. So I get 16 plus or minus the square root of a number. That number underneath is called the discriminant, and 2 times 3 would be 6. Now, if I go through and multiply this out, I'm going to get 256 minus 4 times 3 times 21. I'm going to end up with just 4. That makes it really nice. So I end up with 16 plus or minus the square root of 4 is 2 all over 6. So here's my two equations. So we would have 16 plus 2 over 6, and we would have 16 minus 2 over 6. 16 plus 2 would be 18 over 6, and 18 over 6, of course, would reduce to 3. And the other one would be 14 over 6, which would reduce to 7 over 3. And those are my two zeros. Way to go, Bearcats. Let's go to 1B. Okay, here we again are trying to find the zero. So again, that would be like taking this equation and setting it equal to 0. And I want you to get used to seeing these rational expressions, which are like fractions. If you look at a fraction, and I want you to remember that a fraction, if you have a 0 in the numerator over any number in the bottom, would be 0. And then, of course, we learned in our last half, 0 in the denominator is undefined. So if we want our fraction to equal 0, then we want the top of it to equal 0. So let's go find the 0. So 8x plus 3 equals 0. Subtract 3, 8x equals negative 3. Divide by 8, x equals negative 3/8. That's my 0. Oh, one other thing, because you're in a pre-cal class. Ooh, that made that go away. Is that notice that the bottom of this is going to have a restriction. So we have a restriction that x cannot equal 11 because we would have an undefined term. But our 0 is negative 3/8. Way to go, Bearcats. Let's go on to part 2. All right. The next for part 2, A and B, we are trying to figure out which intervals over the function, determine the intervals over which the function is increasing, decreasing, or constant. Well, let's take a look at decreasing. We're reading from left to right. This part of this graph is going down. It's a negative slope. It's decreasing. This part of the graph is staying the same. It is constant. And this part of the graph is moving upward with a positive slope. It is increasing. So let's talk about what we mean by intervals. If you look at your grid, and I don't have a grid on here. If you look at your grid, you'll have to look at the one on your review sheet. If you'll notice, we stop right here at -1, and we stop right here at 0. So I want to take that as our interval. So we remember, if you keep going, and we're going to assume these graphs go on forever, whether they have arrow on the end or not. And so way out here would be negative infinity, and way over here to the right would be positive infinity. So the intervals for decreasing would go from negative infinity to negative 1. So decreasing negative infinity to negative 1. And I just use soft brackets on everything for intervals. And then we go from, well, if it's a continuous graph. Constant-wise, I'm constant from 1 to 0. I stay the same. So I'm constant from 1. That looks like domain. Sorry, I'm just using abbreviation for decreasing. Decreasing, constant, and increasing. Our interval would be from negative 1 to 0. And then our increasing would be from 0 to positive infinity. All right, let's look at B. Let's look at part B. All right, this function again, it's a little hard to tell from this graph. I'm going to go ahead and draw my axis in here. It may help us a little bit. It looks like that this runs right through our 0. So we're going to say that this is at 1, and then we're going to say this is at 2. I don't really think that may be right. It may be, this may be 2, this may be 3, and 4. I think we'll just say that. Our graph isn't easy to read. On your test, you'll have a graph, a grid there, so you will be able to read those points easier. All right, so let's just say this is the case. So again, decreasing. Our graph decreases. It goes down until this part right here. And then it starts going up to here. And then it goes down to here. Let me make those marks bigger. And then it goes back up. So we've got some key points here. We're going to say that's negative 2. We got to know that our x value here is at 0, and our x value here would be at positive 2. So if that's the case, and we read the graph correctly one more time, this would be a stopping, this would be a change, not stopping, but a change in direction. This would be a change in direction. Then we would have our decreasing. Let's label it, though. This is decreasing, increasing, decreasing, increasing. So we're decreasing from negative infinity to negative 2. We're decreasing again from 0 to 2. We're increasing from negative 2 to 0, and from 2 to positive infinity. All right, hopefully you get that. Way to go, Bearcats. Let's keep going. All right, next we're going to talk about the average rate of change, the average rate of change. All right, there's a little equation for that. It's if you think about what you know about slope, it's very similar. The little equation for average rate of change is f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. And if you think about it, f of x is like a y value. So we have a y minus a y over an x minus the x, which is very similar to slope. All right, they give us an equation, our f of x equation. Our function is negative x squared plus 8x minus 4. And they give us the x sub 1 is equal to 0, and our x sub 2 is equal to 4. All right, the first thing I do is go to my little formula. I always write it down, and I substitute that in. So x sub 2, I'm going to cross that out and make that a 4. X sub 1, I'm going to cross that out and make that a 0. X sub 2, a 4. X sub 1, a 0. All right, I'm going to do the easy part first. 4 minus 0 on the bottom is 4. I know that. Now, I'm going to go through and figure what x sub 4 is. So it's like I have not f of x now, but f of 4. That means I'm going to plug a 4 in for all of these. So I would have a negative on the outside, and then I would have 4 squared plus 8 times 4 minus 4. And if I go through, this is the part that if you're going to make a mistake, it's actually right here. So please be very careful. This 4 squared would be 16, but this negative applies at the after that. So it'd be negative 16 plus 4 times 8 is 32 minus 4. And if I'm not mistaken, I think 16 and negative 4, negative 20. So it looks like we have a positive 12. So this looks like positive 12. So I'm going to say f of 4 is positive 12, and then I'm going to subtract something. I'm going to subtract f of 0. So now I'm going to take this, and I'm going to plug in 0. So I have a negative on the outside, 0 squared, plus 8 times 0 minus 4. All All right, so this is going to become a 0, this is going to become a 0, and I'm left with negative 4. Be really careful. So I have 12 minus negative 4. Be careful about the negatives. So I have positive plus a positive. 12 and 4 is 16. I have 16 over 4, and looky there. That ends up being just 4. Woohoo! Way to go, Bearcats. All right, this next average rate of change, let's write our formula again. We have f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. All right, and then this is the equation that we're given, and we want x sub 1 is 3 and x sub 2 is 7. So again, we're going to plug in. So I'm going to cross this out and write f sub 2 is 7, f sub 1 is 3, f sub 2 is 7, f sub 1 is 3. Now I'm going to do the easy part first. 7 minus 3 is 4. That's what I get in the denominator. So that makes it, I got that part right. Let's keep going. The top is a little tricky. So I'm going to plug in a 7 into this equation. So I have 2 minus the square root of 7 plus 1. I have 2 minus the square root of 8. And I'm going to let you leave it just like that. So I'm going to say that is 2 minus the square root of 8. I'm going to write it 2 minus the square root of 8. And then I'm going to say minus f sub 3. So I'm going to do f sub 3. So I'm going to take the 3 and plug it into this equation. So I have 2 minus the square root of 3 plus 1. 2 minus the square root of 4. Oh, but look, the square root of 4 is 2. So 2 minus 2, that's 0. So I have 2 minus the square root of 8 minus 0. Yay! So here we go. We have 2 minus the square root of 8 over 4. You can leave it like that, or I would love if you would reduce this. So you could reduce this by reducing your radicals. So you could have over here and go 8 divided by 2 is 4, divided by 2 is 2. Pair of 2's, that 2 stays home. So the square root of 8 becomes 2 square roots of 2. So we have 2 minus 2 square roots of 2 all over 4. There we go. And so I'm going to reduce everything. You can only reduce the stuff outside the radical. You can't reduce the stuff inside the radical. So please don't cancel your 8 out. So this 2 becomes a 1, this 4 becomes a 2, this 2 becomes a 1. And so in that case, we would end up with 1 minus the square root of 2 over 2. But I would also take it just like that. Go Bearcats. All right, number 4 talks about odd functions, even functions, and neither, which really relates back to our symmetry if something is symmetrical. So we have an odd function if it's symmetrical with the origin, which would mean we would have to change the y and the x to a negative, and then the equation would have to come back to its original form. And it's even if it's y-axis symmetry, which means we change the x to a negative and it would return back to its normal form. If that doesn't happen, it's neither. There's a few shortcuts, but you have to be really careful. So listen up. It's an odd function if all of the exponents are odd and you do not have a constant. Okay? If there's a plus 5 or something at the end, you have to be really careful because you change part of the equation, but it can't change back because of that constant. It is even always if all of the exponents are even numbers, 2, 4, 6, 8, etc. So those are two rules, but you can't always go by those rules depending on the equation, and we're going to see that in our examples here. All right, so for the first example, A, so for our first example, A, notice all the exponents are even and there's no constant. So a 6, 4, 2. So that is going to be an even function. For B, let's take a look at B. B is a little different. We have 4x times the square root of 3 minus x. And this one can be a little tricky for us. And we could say y equals that. So let's think about if we want to test for even. That's the one you want to test for first. If I make that test for y-axis symmetry to see if it's even, I would have 4 times a negative x and then the square root of 3 minus a negative x. That would change my equation to negative 4x times the square root of 3 plus x. And that equation is not the same as the original. Now, if we were testing for odd, which would be changing the x and the y, we've already changed our x, so let's say we change the y. We make it a negative y equals. Well, if we multiplied the whole equation by a negative 1, let's say, then the y would become positive again, and that matches our original. And the negative 4x would become positive again, and that matches our original. But the inside of the root would not change. We'd still have 3 plus x. And therefore, it would not be the same as 3 minus x. In this case, it is neither. But please don't believe just because there's a square root, it's always neither. It just depends. If that x inside had been squared to begin with, it would have come back to its original form at the beginning. So you just have to kind of watch. You may can hear the rain outside. It's Friday afternoon around 5:30, and it's pouring down rain out there. So that's what you hear in the background. All right, for part C, we have an absolute value, and so let's test it. Let's see, if we test for even, that would be putting a negative x in. We would have negative x plus 5. But that x would just stay negative, and it would make a difference in our result. If we test for odd symmetry, we would make it a negative y equals a negative x plus 5. And if we multiplied through by a negative 1, we would get a positive y, but we get a negative on the outside of the absolute value of negative x plus 5, which is not the same as the original equation. So this also is neither. All right. It's not on our review, but I'm going to go ahead and just show you an odd function and the difference because I think it's important for you to know that. So, oops, I'm going to try to do that. Sneak one in here. So I'm going to just say d, even though it's not on your sheet. What if I gave you f of x equaled x cubed plus x, and then I give you another one, f of x equaled x cubed plus x plus 2. All right, because they're different. This one is a cube root and then a first power. Those are both odd exponents, so you would have an odd function, and that's kind of a shortcut for you. Over here, though, you have to be really careful because this constant, things can't come back to be the same. On this one, if I made this a negative and I made the y a negative and I made this a negative, it would be a negative x, and I made this a negative, it would be a negative x cubed, it would be a negative x to the first, and I multiplied by a negative all the way through, everything would go back to its original form. So it would work. But on this one, look what happened. If I change this to a y, I make this a negative x cubed plus a negative x plus 2. And let's say I make the y negative because we're testing for odd symmetry. So an odd function, which is origin symmetry. Then this would be a negative y, this would be a negative x cubed, this would be a negative x, and this would be a positive 2 still. If I multiply through by a negative, the whole equation, then I would get positive y, I would get a positive x cubed, I get a positive x, and I would get a negative 2, and that's where we get thrown off. That negative 2 is not the same as the original. So you got to be really careful. If it's got all odd exponents, this is the shortcut, all odd exponents, then it's odd. But if it has odd exponents and a constant value, it is not, it will be neither. Okay, that may help clear up a few things. I hope so. Okay, this next one's really, really important, and you all need to make sure you pay attention, and you need to make sure that you get this question right. This is really important information. All right, we have f of 2 equals negative 6. And then we have f of negative 1 equals 3. And we are asked to write a linear function, all right, and sketch the graph of the function. Well, let's take a look at this. First of all, you have to realize you have two ordered pairs here, and I'm not sure you always do. You have to think f of x is a y value. So this is like saying y equals negative 6. And f of 2 is like f of x, saying x is 2. So over here I have a negative 1 and 3 as my ordered pair. So if I have 2 points, I can write the equation of a line. I'm going to write it in point-slope form and graph it in a minute. But right now I'm going to find the slope because I need to find the slope. My slope needs to go right there. So my slope would be y minus y, so I'm going to say 3 minus a negative 6, which is plus a positive, over negative 1 minus 2. So that would be 9 over negative 3, which makes me have a negative 3 slope. So negative 3 is my slope. And then I know this is y minus something and x minus something. And I can pick any point. It doesn't matter which point I pick. I'm going to go in and pick this point, but it doesn't matter. So if I have y minus the y value, which is 3, and I have x minus a negative 1, so that's a positive 1, then that's my equation. So I have y minus 3 equals negative 3x plus 1. That's my linear equation. If you want to distribute and solve for y, you can. If you want a graph, let's take a look at the graph. We can pick one of these points. You don't have to have a y-intercept. Let's pick negative 1, 3. So if I pick negative 1, 1, 2, 3, that's my point, and I know my slope is negative 3. So I'm going to count down 3, and I'm going to count over 1. Down 3 and over 1. And I would be able to graph my line. Woohoo! Go Bearcats. Everybody needs to be able to do that, like with your eyes closed almost. Although don't close your eyes when you're writing because we can't read your handwriting. All right, in these next few problems we're asked to graph them, graph these given functions. The first one is a quadratic, although it's not in the right form. I'm going to write it in the right form. I'm going to write it as y equals. I'm going to put the x first, so negative x squared, and it'll be a plus 3. You can graph by transformations. I would check your graph with a t-table. So if you do this transformationally, you know you're going to reflect over x-axis, and you're going to move up 3. So let's go ahead. Our parent graph would have been just, oh, you need to identify that, y equals x squared. So your parent graph would be here, and 1 squared would be 1, and 2 squared would be 4, and negative 1 squared would be 1, and negative 2 squared would be positive 4. That's our parent graph. We would take each of those points, reflect over the x-axis, and up 3. So this one would go up 1, 2, 3, because it can't reflect. This one would reflect downward and go up 1, 2, 3. Downward, 1, 2, 3. This would reflect all the way down here and go up 1, 2, 3. And this would reflect all the way down here and go up 1, 2, 3. And your graph would look like this. Really good idea to plug in a value and double check it. So let's just check, let's say negative 2. So we'll check at negative 2. So if I take a little t-table and I say negative 2, then I'm going to plug in a negative 2. Be really careful. So you have a negative in front and you have a negative 2 squared plus 3. So negative 2 squared is 4, but that negative applies afterwards. So negative 4 plus 3 gives us a negative 1, and woohoo, I believe that checks out. I would always just double check with a t-table to make sure that you're good to go. And some graphs, like square roots and things, I would automatically use a t-table. That's just me. Okay, next we're going to do a square root function, and this is a negative square root of x. So we're going to make sure that we do this. I think it's easier on a square root just to do a t-table from the beginning. But you could also graph the parent function and do a transformation or reflection if you would like. So I'm going to do the t-table. I know that underneath my square root I can only have 0 or positive numbers. So since it's only x, then I could make x 0, and that would be okay. And if I would have the square root of 0 is 0 and a negative 0 is still 0. So I do know my first point is at 0, 0. Then I could have another positive value, so I'm going to say 1 because the square root of 1 is 1, and I would make that now a negative. So at 1, negative 1 would be another point. Now, you're going to be really careful and pick wisely. So if I picked a 4, I would pick a 4 because the square root of 4 is 2, but then I have to apply that negative, so this would be negative 2. So at 4, 1, 2, 3, 4, I would be at negative 2. And you would keep going if you wanted more points, but those 3 give me a pretty good little curve. Make sure you know square root graphs have a little curve in them. All right. If you were to do anything else, then let's say this was plus 2 out here, then you would take those values, those y values, and added 2 when you solved it in the t-table. I just think the t-table is an easy way on square root graphs. All right, let's look at our greatest integer function. All right, now we're going to be asked to do the greatest integer function. With the greatest integer function, it's really actually is easier to graph this from a parent function. If you are not sure about your parent graphs, look on page 70 in your textbook. It gives all the basic graphs there. The greatest integer function, I'm going to do it in red, the parent function in red, would just be y equals the greatest integer of x. And I'm sorry, I'm not drawing very well. So that would be at 0, a solid dot, over 1 unit, an open dot, up to 1, over, up to 2, over, and it jumps. It's like it's called a step function, this particular greatest integer function, or the greatest integer function is like a step function. And we would go down and over. And it would look like that. So if all we're doing in this graph is moving transformation-wise, we're moving down 2. So I'm going to graph this graph in, let's say, oh, green will make it look like Christmas. We'll graph it in blue. So we're going to move down 2. So I'm going to go back to that original point and go down 1, 2, and put my solid dot and the open dot down 2 and connect them. And then I'm going to take my second one and go down 1, 2, and do it, and down 2, and open and connect them. And now you can see the pattern. So you're just still going up 1, over 1. You've just shifted everything down 2. So down and oops and open. All right, and so this would be your new graph. Not too hard, you just got to really know those starting points. And if you're doing any transformations, you're going to transform, you're going to take this point and this point, move them and connect them. And then you'll probably, after you do 2 of those from the parent graph, you'll see the pattern. All right, let's move on to the piecewise function. All right, we're working on our piecewise function now. Piecewise functions, again, just like the square root function, I would strongly suggest a t-table. I think you'll make a lot less mistakes. So let's go ahead and do the first equation right here. And we're going to do a t-table, and we're going to start with values greater than or equal to -1. So -1 is our first x value. A value greater than or equal to -1, let's pick 0 would be another one. Because this is a linear equation, if you look at that, that's a line. You only really need 2 points to graph your line. So we're just going to substitute in. If you want to do that to the side, you can. So I'd have 5 times -1 minus 3. That's a -5 minus 3, which is a -8. So -1, -8. If I plug in a 0, I have 5 times 0 minus 3. That would be 0 minus 3, which would be -3. -3. So those are my 2 points. You could do another one if you wanted to, but I'm going to stop right there. I'm going to go to my graph. I'm going to go to -1, -8. 1, 2, 3, 4, 5, 6, 7, 8. We'll make it down here. I'll make this long. We'll make it down here. All right. Because this is an equal, I can make that dot solid. So that starting point is solid. You always start your graph and move toward the next point. So 0, -3. 1, 2, 3. And it's a straight line, like I said, because it is linear, and your graph of that part would look something like that. All right, now let's do number 2. So again, I'm going to create a t-table. This says x values are less than or equal to -1. Biggest mistake, you still start with -1. Don't pick a number less, start with -1. We're just going to put an open dot because it's everything less than -1. It could be all the little decimals less than -1. Another number less than -1, an easy one, would be 0. Oh, sorry, not less than -1. It wouldn't be 0. It would be, let's say, -2. Sorry about that. All right, again, linear, so we can just do 2 points, and we're going to plug in. So we're going to go -4 times -1 plus 5. -4 times -1 is a +4 plus 5, which is 9. So -1, 9. And then we're going to plug in a -2. So -4 times -2 plus 5. That would be a 8 plus 5, which is 13. All right, so we have -1, 9, and -2, 13. So at -1 would be all the way up here. I'm just going to say that that's 9. I'm a little off the grid. And at -2, we would be at 13. That'd be up here. And it would be a line, and so this line would go off like this. Oh, I just made a mistake, though. Look at this. There's no equal sign right here, so this would be an open dot. Your first point has to be an open dot. All right, that should be good. Let's keep going. All right, we've got a few more graphs to go. This is asking about parent functions. This is a quadratic, so our parent function is just y equals x squared. T-table for that would be -2, -1, 0, 1, and 2. If I'm going a little fast, you might want to pause and think about what I just did. I'm just creating parent points. So negative 2 squared is 4, negative 1 squared is 1, 0, 1, and 4. And I'm going to go ahead and, since we're supposed to sketch the graph, transformationally, this would be moving down 9. So I would shift down 9 from my parent points. So I'm going to put my parent points in red, which would be a negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. And we're shifting everything down 9. So I count down 9. 1, 2, 3, 4, 5. Oops, let me change colors. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and then I count down 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, look, and that would go over here. And then down 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't think I did a very good job of this, but you'll get the picture. And right here. And so now our graph would actually look like this. So it's a parabola that's been shifted down 9. And that point right there is at 0, negative 9. All right. Next thing is we're going to graph another square root. All right, let's do identify our parent graph. Our parent graph would be y equals the square root of x. And let's go ahead and do our t-table. We know that a square root has to be positive or 0. So we could say 0, the square root of 0 is 0. 1, the square root of 1 is 1. And then remember, we would pick 4 because the square root of 4 is 2. And if you picked another value, you pick 9 because the square root of 9 is 3. And that would be our parent graph. So let's go ahead and do that. And then we'll talk about our transformations. So 0, 0, 1, 1, 4, 1, 2, 3, 4, 2, etc. And now this graph, this minus 7 is underneath the radical, so it has to do with horizontal movement. And remember, anything with x is sort of opposite of what it looks. So when it says x minus 7, we would really be going to the right 7. So we would take our points and go right 7. We'll say that's negative 7. So there's our first point, and we would move right 7. And we would move right 7. Oh, that would probably be, no, I know that's at 4, so yeah, it would be over here. All right, and so then our graph would look something like that. And we moved everything, oh, what did I just do? Oh my goodness, I moved everything to the left even though I wrote move it to the right. All right, well, let's say do-over. Okay, so our points are at 0, 0. 1, 1, and 4, 2. And I would move everything to the right 7, so I would go over to positive 7, and I'd move this, and I'd move this, and my new graph would look like this. Oh my goodness, Miss Zorn is tired. All right, let's keep going. One more to go, guys. All right, we have our last one for this, and then remember, I will post tomorrow the extra practice problems also. Let's see, this is our last, and this is another greatest integer function, so the parent function would have been y equaled the greatest integer of x, and we're going to create that parent graph real fast, and then we're going to do our transformations. Parent graph, remember, at 0, 0 over 1 unit open dot, step up to 2, solid dot, over to 3, open dot, step up, over. You can go down and do the same thing, and down and do the same thing. That's our parent function. Now, let's talk about our transformations. We got two things going on. Nothing is going on with x this time. So nothing's going to happen left and right. This reflection, oops, this negative means a reflection over the x-axis. So we'll flip over the x. And this plus 6 means up 6. So let's see what happens. With our original point 0, 0, we really can't reflect over the x-axis. We're on the x-axis.